Hello everyone. In this video we are going to be looking at factors that can affect the acid and base strength. And we are going to be focusing on the molecular structure. So over here we're going to talk about two types of acid, binary acids and oxoacids. So first, looking at binary acids are essentially protons plus a nonmetal anion. So essentially, the strength of a binary acid is associated with the extent of how the acid can dissociate. And that is dependent on the bond dissociation energy. So between H and A, we have a bond. And then the energy that is required to dissociate this bond is the bond dissociation energy. So if we have a low bond dissociation energy, that means that it doesn't require much energy to break this bond. So it's easier to break this bond, and therefore we are going to have a higher degree of dissociation and a stronger acid. So a low bond dissociation energy between the proton and the anion is resulting in a stronger acid. And over here on the right side are a list of binary acids that can form. We can see that this is part of the periodic table. So if you remember, the right side is noble gas. And then we have two more groups, transition metals, and then all the metals. So this is just a section. So looking into this, remember how we were talking about the charges? So it's 1 minus, 2 minus, 3 minus, 4 minus, right? That's why H is just with one F, HCl, HBr, and HI. Because we have F, fluoride ion is just 1 minus, therefore we'll only have one proton. Same as Cl minus, Br minus, and I minus. And looking at this group, we can see that, well, oxygen was 2 minus, S was 2 minus, selenium 2 minus, tellurium 2 minus. Therefore, we're going to have 2 protons because we need 2 pluses to balance the charge. That's why it's H2O, H2S, H2Se, and H2Te. So similar idea, nitrogen is 3 minus, phosphorus is 3 minus as well. Sorry, phosphide and nitride ions are both 3 minus. Therefore, we're going to have H3, H3. And carbon and selenium falls into the 4 minus group. That's why it has H4. So let's look at the trend. So as we are going across the periodic table, we are determining the relative strength based on the polarity of H and A. So remember how bond polarity works? So polarity is associated with electron negativity, which is the tendency of something to attract electrons. So if we have a stronger attraction to electrons, then we have a higher electron negativity. And in general, looking at the periodic table, our electron negativity increases as we go to the upper right-hand corner. So increase electron negativity. So if we have a nonmetal with a high electron negativity, that means that this nonmetal is going to attract the protons closer to itself. So we are going to have a polar bond, and it's more polar because it has a higher electron negativity, which means that, well, the electron is already super close to A. So we can imagine that we have HA. Nonpolar means we are sharing the electrons evenly. If A is a higher electron negativity, then A is going to have the electron attract closer to it. If A has a super high electron negativity compared to B over here, then we can see that since the electron is already so close to A, then it is going to be easier for the electrons to completely transfer to A to form H plus and A minus. So that means that the bond between H and A is weaker, and therefore it has a low bond dissociation energy. And if it's weaker, it's easier to break, and it's going to result in a stronger acid. So that means that coming back to our periodic table trend, since as we can see below, over here we're comparing across the periodic table. So CH4, NH3, H2O, and HF4. So it's these four. We can see that between H and F, H2 and O, the electron density on H is so much smaller when we are in HF compared to when we are in CH4, where they're basically shared evenly. So remember how we can interpret these electron density maps? Well, the purple one is low electron density, and then red is high electron density. So you can see that for fluorine, because it's on the upper right-hand corner of the periodic table, so higher electron negativity, it's attracting all the electrons to it, leaving H with super low electron density. So it's going to be a stronger acid compared to H2O, where the electron density on the H's are low and on the O is high. But O has a lower electron density than F, so its attraction is going to be smaller. And then looking at the extreme case CH4, the electron negativity differences between C and H is very, very small. That's why over here you can see that the entire bubble is green because the electrons are being shared evenly. So to conclude, going from left to right to the periodic table. So going from left to right of the periodic table, we are increasing the electron negativity of A. Therefore, we are increasing the acid strength. So we have a strong acid on the right and weak acid on the left. And let's look at going down the periodic table. So as we're going down the periodic table, the major determining factor is the size of A. So last time we compared going across the periodic table, now we are looking at going down the periodic table. So within the same group, we can determine its ion size. So the size of the ion, so remember back in the days when we were learning quantum mechanics, we have the shell number n. So this is n equals to 1, n equals to 2, n equals to 3, and then n equals to 1, 2, 3, 4. So as we have go down the periodic table, we went from n equals to 1 to n equals to 2, n equals to 3, n equals to 4, n equals to 5. This is when we were looking at quantum mechanics. So for F, it's going to be smaller than I because I has more shells than F. So this is just looking at the shell number. So if we have a larger nonmetal, then that means that we are going to have a weaker bond. And you can imagine that because we're bigger, so let's look at I is this big, H is this big, so they're further away from each other compared to when it's F and then H and F. Okay, I'm totally exaggerating this, but looking at the distance between H and I and H and F, you can see that H and I is further because I is bigger. So if it's larger, then it is going to have a weaker bond, lower bond dissociation energy, and therefore resulting in a stronger acid. So if we have a large ion, then we are going to have a stronger acid. And this is, okay, I just noticed it's right at the bottom. I don't know why I was drawing it. So over here you can see that for HF, F is small, so the electron density is, the differences between electron density is smaller compared to HI, where it is bigger. So the acid strength is going to be stronger for HI because it is having a smaller bond strength. So we can conclude that as we go down the periodic table, we are increasing our acid strength. So the strong acids are on the bottom, relative strong acids, and then the weak acids are on the top because the size is bigger down here. So weak acid. The next category that we're going to talk about is the oxoacids. So oxoacids, as its name suggests, it's an acid that contains oxygens. An example includes carbonic acid, nitric acid, sulfuric acid, and then we also have the hypochlorous acid. The general formula of oxoacids is as over here. So we separate them into O's and then OHs. So looking at this, well, let's try writing it for one of them. Let's try writing it for carbonic acid. So carbonic acid is this one. We can see that it's O. There are one O, so it's O1. And then the Y is the carbon, so over here. And then OH, two of them. So that is the general formula for oxoacids. And then after we clean it up, it becomes H2CO3. So over here, this is the reason why I want to introduce this general formula is because the number of O and number of OHs does matter later on when we're looking at how we can determine this string. Looking at the first case is when we have the same N and M, so meaning that we have the same number of O's and OHs attached to Y and different Y. So looking at this case, then we can see that over here, the case that we're looking at is down. The second case is if we have the same number of Y, so the same core atom, but different numbers of N and N.